Good day. In this video, we will talk about the work done by a varying force. So before we talked about what would happen when you apply a constant force, and this force makes this object move a certain distance, and then you have this displacement. If I plot the force, force, and then position X, we're in the X-axis. This is the force in X. So what we see is that the force, because this is a constant force, well, the force is constant. We also said that the definition of work was, this is too thin. The definition, no, here, too thin. The definition of work is force dot that and or F delta R cosine of theta. Well, notice that in this graph, the product of force, which is the vertical axis, and this here is delta R, right? So multiplying these two, they are parallel, so this is 1, basically. So F delta R, this is F, this is delta R. What happens when you multiply F times delta R? You get the area under the curve, and which is the work. So the area under an Fx curve gives you the work. So what happens now if the force you are using to move your object, let's say, is still in the x-axis, but this force is changing with time? So at every little location you have a different force. Let's say the force varies like this. Well, it's not constant anymore. We cannot use this equation, but we can still use this trick. If we were able to find the area under the curve, we would still find the work. Of course, the area under the curve is done with an integral, which I am not going to explain here. I'm going to let your calculus teacher do that, because we also are not going to use this. I'm just telling you the formal way to do it is through an integral, but we can also do it graphically by just analyzing the area under the curve. So let's say our force is changing like this. This is force as function of position, not force as function of time. So if this is the force we have, let's do the example and try to find the work done by the force on the particle as it moves from 0 to 6. So from 0 to 6. So all we have to do is find the area under the curve, which is going to be the area of this rectangle. So 5 times 4 plus the area of this triangle, which is 5 times 2 over 2. So this gives us 20. This gives us 5. So the work will be 25 joules. Nice, that was simple enough. Let's now consider a very good example of a force that is changing all the time. And that is the force of a spring. Force done by a spring. The force done by a spring is not constant. If you take a spring, actually I'm going to use this drawing. We have a spring. Let's consider first position B. At this position, the spring is not stretched nor compressed. It's the natural length of the spring, and the spring is doing nothing. At B, the spring is doing nothing. Now let's consider A. If somehow this block is moved to the right of this point, which we call the equilibrium point, if the block is to the right, notice that the spring tries to go back to its original position, the neutral length. So it's going to pull on the block. So when the position of the block is positive, the force is negative. On the other end, if somehow the block makes it to the left of the equilibrium, then the string tries to restore its position by pushing to the right. So what we see is positive position, negative force. Here we see negative position, positive force, because it's pointing to the right. But if we plot this, we notice that as we move to the negative x, the forces are positive, and if we move to the positive x, the forces are negative. Experiments show us that the force behaves linearly. Like if you were to perform an experiment, you will see this type of behavior, a linear curve. Linear as in y is mx plus b, right? That's the equation of a line, but turns out this is a negative line, well, negative slope that also passes through zero. So b is zero, right? The slope m is negative, right? Negative m, and basically we're going to call it k, right? And then that's it. The x-axis is the force. Sorry, the vertical axis is the force, so y is the force, and the horizontal axis, well, is x. So then we get the equation of a curve of this line, y mx plus b is force negative k x plus 0, or simply, oh, sorry, if we simplify this as the force exerted, and I'm going to put it like this, Fs means force, well, it's here, done by a spring, or exerted force exerted by the spring on the block. Okay, that's important. It's going to be negative kx. This is known as Hooke's law, and well, this is a good example of a force that is not constant. As you can see, the force is changing with position. Now, if we want to know the work, well, remember, all we have to do is find the area under the curve, and in this case is a triangular area. So let's find the work. So I erased a bit of stuff. We start with the basic equation. We understood that to find the work, we need to do the area under the curve, which is base times height over 2. So the base is the position, right? Position maximum, as is written here, all this. The force, well, the height, well, is the force, right? And that's over 2, because it's a triangle. Well, now if we combine, if I plug this here, I get position maximum times the force, but the force is minus k times x, which is also the position maximum, because we're talking about the force here, which happens at x equal maximum over 2, right? We're gonna get that the work is 1/2 k x squared. You're gonna say, what do we do with the negative sign? I'm going to tell you, ignore it for now. Let's focus on the number here, on this expression, and then I'll tell you how to define if the work is positive or negative, because it can be positive or negative. So first of all, let's consider this. This is the magnitude of the work done by a spring, which is why I'm going to put the S. This is work done by the spring on the block. Okay. Now, how do we find if the work is positive or negative? Well, there is a very simple way to find this. If you have the block and this is the spring, let's say the spring is compressed, and then what happens is that the spring pushes the block to the right. Notice the force of the spring is pointing to the right and the displacement is also pointing to the right. So the work is positive. Right? Because of cosine of theta is cosine of 0. So cosine of 0, so this gives you positive 1 and the work is positive. Imagine somehow that now you have this scenario in which the block, for whatever reason, is moving towards the left on an unstretched spring, and then this is compressing. The motion of the block is compressing the spring. So your final position is like this. By looking at this, we can see how the displacement is to the left, but the spring at all times was pushing to the right, right? So towards whatever equilibrium position, let's say this was the unstretched position of the spring. So as it got compressed, the spring wants to push back to go back to its original unstretched length. Notice then how the force is pointing to the right, the displacement is pointing to the left. There is an angle of 180 degrees. So the force and the displacement are anti-parallel, and that means cosine of 180 equal minus 1. So the work is negative. So what matters is that you understand how the displacement vector and the force vector compare. The direction of both of them. You need to see what is the angle to know if the work is positive or negative. And in both cases, we were talking about the work. This is too thin. The work done by the spring. Let's consider this scenario now. I am going to use an external force to move the block from this position to this position. The 0 is here, so you notice that the displacement was towards the left. All right, this is the equilibrium point, neutral length. So what happens if I calculate the work done by this external force? Well, first I need to understand that there are two forces at play here. The force on the block, the external force done by me, and the force done by the spring. Notice that the work done by the spring is negative because the displacement comes to the left and the spring force goes towards the right, so 180 degrees. But notice that the work done by the external force is positive. Now, if I make this move very slowly at constant velocity, a free body without friction, of course, then the external force is equal to the magnitude of the external force is equal to the magnitude of the force. And what we see is that, well, the work done by the external force is going to be the negative, because it's positive, to whatever the spring did, right? So the work done by the external force is the negative of the work done by the spring. In the next video, we will see what the work done by a spring and an external force look like from any random position to another.